Good morning, Jakob. Thank you for
Good morning.
joining us. It's early morning there, but we are very delighted to have you. Uh, yeah, just let me give you a short introduction about Jakob. Dr. Jakob Heier received his PhD in material science and engineering from Cornell University in 1999. And since 2006, he's working at Empa, which is Swiss Federal Labs for Material Science and Technology, in the laboratory of functional polymers. And today he is heading the group of functional thin film solution processing and leading the wet coating and printing activities in the Coating Competence Center of Empa. And his current research focuses on two aspects of functional coatings. One is investigation into 2D materials as functional ink for advanced electronics and photonic devices. And the second is development of printing technologies to meet the needs for printed electronics. So he will talk about MXene-based inks and also high-resolution Gravure printing. So thank you, Jakob. Thank you. You can start.
Thanks a lot for the invitation to this presentation. I'm looking forward to and welcome to my presentation here. I will talk about I call printing the future. So I will actually catch up on a couple of topics of the previous speakers. As you may see in the background of my camera, the sun has raised up here in Europe, so it's getting like normal working time. So what I'm going to shortly introduce you is to Empa and the Coating Competence Center, which we built. And then two of the topics we mainly work on. One is a project on high-resolution gravure printing, as was introduced, and the other one on inks based on MXenes. And then finally a short outlook. So Empa is a materials research institute within the Swiss education system, the Swiss federal education system that consists of two universities. So the most famous one is ETH Zurich, and connected to this are four research institutes, whereas Empa is one out of them. So we do research that serves society and the benefit of society in four research focus areas. One is nanoscale materials and manufacturing technologies, built environment, health and performance, and energy resources and emissions. So on the manufacturing technology side, we are working on sustainable manufacturing technologies. And in that framework, we opened the Coating Competence Center about 10 years ago. So the idea is to provide instrumentation to develop competences through research projects and then offer these competences to partners in academia, but also to the Swiss industry. So we are not only working with printing and wet coating technologies, but also sputtering, chemical and physical vapor deposition and others. So we are responsible in this Coating Competence Center for wet coating and printing technologies. I just show you the instruments we have. So we are starting at digital printing techniques from 3D plotter to electrohydrodynamic printing. So they are all characterized by different type of applications, different type of possible resolution, but also different type of properties of the ink. So starting at very high viscous inks, very low resolution with our 3D bioplotter, but going down to 100 nanometer features with the electrohydrodynamic printing. So we also do coating, slot coating and spray coating. And as Michael Schläfli introduced, we also have an NSM like the first model of the C650, by then called C600, installed at the Coating Competence Center. So we have a gravure printing unit, a flexo printing unit, screen printing unit, and also a comp nozzle dryer developed by KIT in Germany. So short words on printed electronics. We are all more or less from the field, so we know all about the complexity, the challenges, and the expertise that is needed to work on that topic. So from materials to device physics, there are a lot of different challenges in between. So the material you need to formulate as an ink, like depending on the printing technology and the hydrodynamics that are involved in the deposition techniques, you need to adjust the rheology of your inks. Finally, how do these wet coatings and films form or dry or form like a film also significantly influences device performance. So we work on all of these topics. What I picked for the presentation today is like on one of the printing techniques that we help to develop, that is gravure printing on the Schläfli machine. The other topic will be on the material side, and here I want to show like the potential of MXene inks. So as I said, I catch up on previous speakers. So Michael Schläfli introduced like the gravure printing unit on his machine. Also MXenes have been introduced by the previous speaker. So as also already mentioned, like our project on gravure printing is called Scalar. It's a project funded by the ETH domain in a funding instrument called Strategic Focus Area Advanced Manufacturing. This funding tool supports research that needs expertise from different fields. So it actually needs like at least 3 academic partners from research and universities of the ETH domain. So we have 2 laboratories from Empa, 2 laboratories from EPFL, and 1 from ETH Zurich contributing to this project. Also, the chances for project funding increases when you have industry partners within this project. So here also Schläfli AG is one of our partners next to 3D AG and Dettweiler. So what we want to do in this project actually is we want to make gravure printing fit for printed electronics. So gravure printing is a very well-established technology from the print media industry. If you now go to the requirements of printed electronics, you will see that they are much stronger. So you cannot go from a dot pattern with a medium resolution that's kind of adapted to the resolution of the human eye. You need to go to higher resolution. You need to be able to print defect-free films. You need to be able to print defect-free and very well-defined lines. So I'm almost a bit scared. I show like an image of a publication of one of the previous speakers, Gerd Grau. He was one of the, like actually already 10 years back, he was greatly contributing to the understanding of gravure printing. And I think his PhD supervisor is now professor at EPFL, so also ETH domain, and he is actually also part of our project. So I would be happy to also get feedback and comments from your sides then. So anyway, to really make gravure printing fit, you need to first of all understand the process. So gravure printing sounds fairly easy. So you say like you engrave a cylinder and fill the cylinder with ink, and this image or like this ink is then transferred to a substrate. But indeed, it's a more complicated process, and it involves 4 major steps. One is filling the cavities in your gravure cylinder. Second step is wiping the excess ink off. The third one is in the actually ink transfer or ink splitting process. And the fourth one is spreading of the ink on the substrate, and that will form your final figure. So each of these processes now has certain requirements or can be optimized for an ink. So one of the findings of the group of Subramanian and the work of Gerd Krausen was, if you take like one characteristics of ink in the printing process, which is in a capillary number, which contains surface tension, that contains viscosity, but also printing speed. For each of these capillary numbers, you will see that one of these 4 processes is actually limiting ink process, so the ink transfer process. So the big challenge in this project now is actually how do you optimize what kind of ink, what kind of printing conditions do you need to optimize all these 4 processes that are involved at once. So actually the approach in our project was we were digging in the literature. Conclusion number 1 is you cannot go to infinities high resolution with gravure printing because you're limited by several hydrodynamic factors. But in practice, gravure printing today is limited by the resolution of the engraved itself. So in the graphic arts industry, this is typically done by electromechanical etching. So you do not need very high resolution. 20, 30, 40 microns are enough. What you can actually do today, you do direct laser engraving of the cylinder that goes down to resolutions of 4 micrometers. What you actually want to have at gravure printing is you want to go somewhat lower. So in this project, what we actually develop is a fundamentally new process for cylinder structuring, which I will talk about soon. The other part of this project is that we really try to understand how can this interplay of ink rheology, cell geometry of the cavities, and also the processing conditions be harnessed to make use of these hydrodynamic forces at play to optimize like printing resolution. Now, what we do in Scalar, we actually do not engrave the cylinder directly, but we laser pattern a polycarbonate foil. We do this on a model pattern where we can implement a lot of different features to really understand where is the optimum. So in this pattern, we actually have something like 170 different configurations of cell shape, of aspect ratios, of periodicity, and aspect ratios. So this is done at Empa by high resolution laser ablation into a polycarbonate foil. Then the 3D AG is mainly busy with security printing. They do a pattern transfer into a nickel shim by electroforming. This one then is laminated and welded onto a gravure cylinder. And parallel to this, what also Michael Schläfli mentioned before, they did some improvements like on the software and the hardware side to our gravure printing unit. And then at the end of this project, we're actually currently busy with, we're doing printing and evaluation of all these different features that we can print with this unit. So this is a slide of Michael Schläfli again, what were like really the mechanical and software improvements of this machine. So what we implemented is like force measurement between the gravure printer, between the gravure cylinder and the substrate. Also force measurement between the blade and the cylinder implemented with a feedback control. So we actually can guarantee that we have the same forces during the entire printing process. This is an example of the mask. So this is high resolution printing with a UV laser with 240 nanometer nanoseconds. That laser can go down to 2 nanometer feature sizes. What I show here is an example of one of these features, one of these test features, which we realized. So we vary the periodicity and we vary also the size of the cavities, and we have some different test patterns where we measure conductivity, where we also can measure individually the ink transfer. So how we do the evaluation, what we're actually looking for are scaling laws and the smallest features we can achieve. This is how kind of examples of this evaluation. So we are not only interested in perfect pattern transfer, but we're also looking at which conditions do we actually implement a lot of defects. And what you see on the middle graphic here is that we indeed can find scaling relations when we find like certain parameters in this printing process. So what we actually have by now, we have something like 20,000 images which you have to analyze. So I cannot show yet the results, but in future you can look at our communicate with us or look at our publications, and we hope that we can really greatly contribute to an understanding of especially how does cell geometry, how does this influence and affect like the fidelity of the gravure printed pattern. So we are also after what are the smallest line features we can print. We also have not found the smallest features, but currently like 8 micron is a very, very reliable conductive line from a silver nanoparticle ink, which we can print. Okay, now I want to move to the, or switch to the next topic. These are the MXene inks. So on the material side, they have also been already introduced by the speaker before me. So you all know graphene from mainly the graphene flagship. We know they're suitable as ink for printed electronics. So the MXenes, they actually stick out for their compositional and architectural variety. So they're transition metal carbides and nitrides. What you actually now can do, the transition metal can be any of these transition metals that are indicated in violet here. These materials can be functionalized with a lot of different functional groups. So the backbone is carbon or nitrogen, or even mixtures of that. So you cannot only mix like one element, but you can also mix different elements. So you can make solid solutions. You can order disordered double layer structures. You can make sheets of different thickness, and also what people are currently working on are the so-called high entropy MXenes, where you introduce more than 4 or 5 of different transition metals into one of these MXene layers. So they mainly stick out for metallic electrical conductivity based on the transition metals. What makes them very interesting for sensing and also energy storage applications is a very, very high electrochemical active surface. What you now actually can do via composition, you can tune work function, you can tune conductivity. So materials are actually also very strong as a 2D material. And most importantly for our field, they are easily processed from their colloidal suspension, so they are exfoliated in solution, and you can make inks from them. Now, as I said, you can control like their properties via composition and structure. So if you actually look at how many of these different MXenes are possible, you're in the range of a couple of thousand actually, and that can really lead to a paradigm shift in like the field of printed electronics, because what you now do, you make building blocks from individual molecules, and you have inks, and you put them together as like a functional device. So that actually led to a field called mexatronics. These are all very early research results from solution deposited, not yet printed applications. But in this review article here, it's shown that these MXenes actually perform very, very well in all kinds of different devices. And what I actually now want to introduce is an Empa internal research project. So as I said, there are plenty of applications of the MXenes. So in the field of electronics, sensors, catalysis, energy applications, electro-optics, environmental applications, also biomedical field. So the Empa direction realized this actually fits very well with most of the research focus of Empa in nanoscale materials, health and performance, energy resources and emissions. And they fund the project where we can really look at basic properties and find a lot of different applications within the competences of Empa. So again, this project is favoring collaborations within our institute. So we have a laboratory working on atomistic modeling. So they look at the properties, electro-optical properties of different MXenes. They look at stability of the precursor max phase. They look at the possibility how can these materials exfoliated. Then we have a ceramic laboratory that is now actually synthesizing precursor max phases, also high entropy MXenes. Our lab is wet coating specialists. We are working on the exfoliation of these materials and also printing of devices. And we have another laboratory that's specialized on post-treatment and characterization of nanomaterials. So at the end, what we establish here at Empa is a platform for MXene research where we find correlations between the structure and the property, and we also identify properties of MXenes that we can make them, that we can apply them for different applications that are currently researched at Empa. So I just want to show a couple of examples what we've been doing and have been achieved in this project, also in the field of printed electronics. So MXenes stick out for very, very high, like almost metallic conductivity. So what we were looking at, if via a slot die or coating process, can we replace transparent conductive electrodes, like for example ITO, which is needed for solar cell applications. It's also needed for displays. It's also used in any smartphone application, any type of display. So for that, what you need high conductivity and you need transmittance. And actually, if you dive deep into the physics of electro-optics, you will see that conductivity and transparency are correlated to each other. When you draw, you will find like this theoretical curve here that plots transmittance versus like a measure called sheet resistance. And there is one variable in it called figure of merit. The higher this value is, the further you will shift this curve to the left, and the higher also the performance of this material is. So
sorry, Jakob, excuse me for interrupting you. It's just 2 minutes left
2 minutes?
from your time.
Okay,
Yeah,
I quickly go to the project. Thanks a lot for joining me. Anyway, what we could show, like with these MXenes, we can actually, by just varying the size of the particles, we could increase this figure of merit from 4.5 to 2.1. I actually could not believe, and I think this also addresses a question of from the previous talk. How can you actually align and how do you actually put these what's actually the quality of like one of these 2D material layers, and what we actually see here, an AFM image of like one of these slot die coated samples, and you can really reliably like deposit these films that you get like something like an average number of layers of 1.8, and you see there is substrate coverage of 97.9%, and half of your substrate is covered with 2 layers and 1 layer, and correspondingly like then you fill up the rest with 1 layer and 3 layers. So these are examples what kind of devices we can then make with this. Then we also go to the field of printed supercapacitors. Like very strong interactions between these MXenes actually lead to very, very high viscosity inks already at low concentration. So that's very suitable for screen printing, extrusion printing. So here are examples how we print supercapacitors, also similar to the previous speaker. We also adapt these inks for gravure printing. So the issue is we want a lot of material inside an ink at low viscosity adapted to this printing technology. So what we actually do, we do solvent mixtures. So we stabilize like MXenes ink like covered with water in like a polypropylene solution. And these are also again examples of gravure printed devices. So we do heaters, we do supercapacitors, we do transparent electrodes, we also do LEDs. And like it's an outlook. So I think just two words, like both gravure printing and MXenes, we believe have a very, very huge potential that they will play in future in printed electronics. With this, thank you for your attention. Thanks to my co-workers and also thanks to the funding agencies.
Thank you so much. Thank you, Jakob, for your very nice presentation and talk. So, questions from audience here? You.
It's very interesting talk. Thank you. I really interested in the MXene for the printing because normally we use ITO for solar cells as the transparent electrode. Now, how to compare their, bending test, how robust this compare with the commercial available ITO substrate?
Yeah, thank you. Very good point. So we did bending tests. If you look at the presentation, at the publication, we actually did 10,000 bending cycles of one of the substrates, and they perform extremely well. So that's a huge advantage over ITO actually. So they're very suited for printed and flexible electronics. But this figure of merit, like we cannot reach ITO. So actually, we now develop strategy to make a gravure printed silver grid and coat that with MXenes, and then you actually come very close to the numbers of ITO.
In terms of the cost, we want to use the transparent for large scaling. In terms of the cost, it's comparable with ITO, or in what the range of the cost you can predict in the future for the commercial product for the MXene as a transparent electrode?
In the moment, it's research stage, right? I mean, you need to start at the max phase. You also need to sinter. You need to do chemical etching. You need to do exfoliation. In the moment, it's still very expensive, but there are a lot of efforts to actually try to upscale synthesis of MXene. I believe it will be another 10 years, like similar to the efforts to make graphene production cheaper.
Thank you so much.
Question from audience online. Oh, hello. Hello, can you hear me, Davide?
Yes, I can hear. Can you hear me?
Very, very welcome to meeting. Yeah. Do you have any question from Jakob?
Yes.
Yeah.
I have a
Okay,
question,
please,
Jakob.
please. Please.
It's a fantastic presentation, Jakob. Very, very interesting. Going back to the first part of your presentation in relation to gravure printing, you are improving progressively the resolution of gravure printing. What film thickness at this higher resolution are you achieving now in terms of depositions? Because typically smaller cells means lower maximum volume depositable.
Correct. That's also one of our efforts that we want to optimize actually the portion of material of ink that we transfer from the cavity onto the substrate. So we're in the 100 to 200 nanometer range max. What Michael Schläfli also mentioned, like the C600 has an extremely good overprint accuracy. So what we actually also do, we do 3-4 overprints of structures, and then we can go to much higher features, depending of course on what kind of lateral resolution do you have, right? But if you want to print 20 micrometer wide lines, we can go like into the micron range.
Thank you again, Jakob, for being with us and contribution. Thank you very much. And yeah.
Thanks a lot.